In this lesson today, we're going to be learning more about exponential and logarithmic functions. And it's really our first investigation into what is a logarithmic function. So when we talk about exponential functions, we know it's a function with a base b and x is an exponent this time. We've talked about whether it's exponential growth or exponential decay, and that depends on what the b value is for that base. But it's always a one-to-one function. So it has a domain of all real numbers or negative infinity to infinity. So if it's one-to-one, then it has an inverse function. And that inverse is going to be a logarithmic function. So let's graph really quickly what the exponential function 2 to the x looks like. So every exponential function will have the same kind of shape, but the base will kind of change how it's growing or decaying. So if we did a table for this and did y equals 2 to the x, and if x was 0, 2 to the 0 power is 1, because anything to the 0 power is 1. So I know that we're going to have a point at 0, 1, and then we just start putting in our points. So 1, 2 to the first is just 2. So I'm going to have a point at 1, 2. And then 2 squared. If x was 2, we get 4. So 2, 4 is a point. 3, 2 to the third power is 8. So I have a point at 3, 8. We could keep going. It would be 4, 16, 5, 32. So you're just going to keep doubling in our pattern. If I went to a negative 1, 2 to the negative 1 power uses that negative exponent rule. So it becomes a fraction, it becomes 1/2. So I'm going to go to negative 1, positive 1/2. Then we can go to negative 2. We see 2 to the negative 2 power is 1 over 4, because 2 squared is 4. If I graph that, I'm a little closer to the x-axis. And what we see is as we keep going back negative, it's going to get closer and closer to the x-axis. So at negative 3, we'd be at 1/8, then 1/16, 1/32. So these are just going to get very close, and it's going to look like they're actually on the x-axis. That's just because they're so close. And then we grow very, very quickly, because that's what exponential functions do. So when we look at that, we see it has a horizontal asymptote. Horizontal asymptote at y equals 0. Every exponential function will start out like this. Depending on what the base is, it will either be growth or decay. So if it was 3 to the x, it would still be growing, but it would just grow faster. It would still have that horizontal asymptote, 4 to the x, 5 to the x, whatever we have. If it was 1/2 to the x, then we saw that decay function. All right, now if we were to graph the inverse of this, our inverse is a reflection across that line, y equals x. So let's put in, what would the inverse point be? So the inverse of 0, 1 is 1, 0. The inverse of 1, 2 is 2, 1. The inverse of 2, 4 is 4, 2. And then we had a point at 3, 8, so its inverse is 8, 3. But this point back here is negative 1, 1/2. So its inverse is 1/2, negative 1. So I'm going to go to 1/2 and go down to negative 1. Our inverse here was negative 2, or sorry, the point was negative 2, 1/4. Its inverse would be 1/4, negative 2. I'm going to go to 1/4 and go down to negative 2. So what you'll see is as we get closer to the y or x-axis here, it's getting more vertical. It's going to get closer to the x-axis. All right, and so we see a vertical asymptote. And then it goes off to infinity on the right. So there's our logarithmic function. It has a vertical asymptote at x equals 0. But we would write this function, this is y equals log base 2 of x. The original function was y equals 2 to the x. So those two things are inverses of each other. What we want to do is investigate, what does that look like? All right, so we had f of x was 2 to the x, and then our new function, f inverse, is log base 2 of x. So what we'll notice is that the bases stay the same. The base of the exponent becomes the base of the log. And then here we have our input. Our input was the exponent. F of x is our output. And when we find an inverse, we've swapped them. So now the output became the new input. And then what was the input became the output, because we're working backwards. So if we showed that relationship as far as a mapping goes, whatever we have here in the inputs, it's finding an output. So I'm going to use that function f of x equals 2 to the x. And let's do a point that I didn't plot. So let's say I plug in 5. When I put that into my function 2 to the 5th, I'm going to get out a 32. What the inverse does is takes that 32 and plugs it into the log function. So that would now put into the log 32, and I would get out a -5 again. So we would just write this as, down here, 2 to the 5th became 32. So that input was 5, the output was 32. When I swap and do the inverse, now the input is 32, and the output is the 5. So what we want to do is try to work our way to convert between exponential and logarithmic form. So if I have 3 to the 2nd power equals 9, we want to convert it into logarithmic form. One thing that's always going to stay the same is the base. So if it's base 3 of the exponent, it's base 3 of the log. And now the input was 2, and the output was a 9. So the new input is going to be 9 because we swapped them. So that becomes the input. And the output is the exponent 2. So if I convert this one to logarithmic, the base is still the same. It's a base of 4 for the exponent, so it's log base 4. Our input of the log is what was the output, so it's 1/16. It should equal -2. So the inputs and outputs have swapped. All right, now that was our input, and we got out the exponent. So logarithms are a way to represent exponents because they get really big when it's in exponential form. If we have b to the x and just do it in general, b is our base, so it becomes the base of the log, and we write it out as log base b of a equals x. So it was the input, became the output of the log, and what was the output of our exponential became the input of the log. So this is our general form, and we're going to be going back and forth between these two from exponential form to logarithmic. Okay, In the second page, we're going to be using those two forms. So if we're converting, we have exponential form here and logarithmic form there. It's important to know how to read that. So when we get to log, we say log base b of a. So the a is what we're taking the log of, and then it's equal to x. B is always a subscript, so you're going to want to write it as a smaller number under, like kind of underneath the log. So when we convert these, I would say this is going to be log base 5, because it's a base of 5 for the exponent, and then of something. So if we were base 5, it came out to be 125, so that's what's going into the log. So log base 5 of 125, and now it equals 3. So we're just converting into that logarithmic form from exponential. Number 2, kind of same situation. We have 7 to the negative 2 power equals 1/49. Negative exponents flip the fraction, so that's what happened. But we would turn this into log base 7, because that's the base of the exponent, of, and what's going inside the log was the output, so that's 1/49. And it should equal negative 2. Let's try this one again. So log base is 9, and then of something. So what goes inside the log is the output of the exponential, so 3. Log base 9 of 3 is equal to 1/2. And then go ahead and try number 4 on your own. You can pause the video and then see how it would switch. All right, so you should have gotten log base 1/4 of 64, and it's equal to negative 3. If we go backwards, we're going from logarithmic to exponential. So now we want to convert and say this was a base of 2 in the log. So it's become the base of the exponent. So 2 to some power equals something else. And we want to figure out what is that power. Okay, and so if we look at the log, the output is a 4. So now that becomes the input of our exponential. So 2 to the 4th equals 16. We turn this one into exponential for number 6. We have 3 to some power, and since it's a base of 3 in the log, it became base 3 of our exponential. So 3 to the 3rd power equals 27. All right. The last two, go ahead and pause the video again and then try these out on your own as well. So you would have gotten 6 to the 1st equals 6. And then square root of 11, that squared equals 11. We have a few special logs. The first one is a common log. This common log is a log with a base 10, and it's denoted by omitting the base. So if you see a log without a base, it means automatically it's base 10. So let's just write that out here. So if a log doesn't show a base, it is base 10. So if I convert these, I have 10 to the 4th equals 10,000. Let's convert to log. So log base 10, we don't have to write the base if it's base 10, of 10,000 equals 4. So I'm not going to write a base here because that's a common log. It's just implied that it's base 10. Same situation here. It becomes log of 10 million equals 7. All right, this one, it's already in logarithmic form, so we want to switch it out. Because it doesn't have a base, it's implied it's base 10. So if it's helpful for you to write that in there, you can, but it's 10 to the -1, and it should equal the 1/10. Last thing here, so again, no base is written, it's base 10. So 10 to the 3rd power equals the 1000. The second one of this is called a natural logarithm. So a natural logarithm is base e. In that case, e is an irrational number. So we had in our calculator a button that has the pi button there. If you see in that pi button, there's also an E and an I. So if I'm going to press the pi button once, I hit pi. But if I hit it twice, I get E. And it's approximately this value, 2.71828. And it keeps going on forever. There's no pattern to it. It's irrational, so it just keeps going on forever. But it's a naturally occurring number that we see in nature and other mathematical situations. So it becomes super useful, but we created a special log name for it. It's called a natural log, and it's just ln of x. So if you see ln of x, it's a log base e automatically. So I'm going to convert. If I converted this way, this would say log base e, because that's the base of the exponential, of 2 equals x. But you're not going to see log base e ever, all right? If it's log base e, it's just automatically natural log of 2 equals x. So same situation here. If I want to write a log base e, I can, but log base e is the natural log. So natural log of 45 equals x. All right, we do this one. This becomes the natural log of 1/12 equals x. If I want to go out of a natural log, we're going to use the exponential form. So I'm just going to rewrite this as log base e so that we can see what's happening. But just know that we don't ever see it written out as log base e. So you would see it as natural log of 15. That means if I'm converting, our exponential is a base of e, and it's to the x power, and it should equal 15. Same situation here. That is a log base e. So when I go to exponential, its base is an e. We're going to raise it to the x power, and it should equal what's inside the log, which is 2/3. Last one here, so it says e to the x power is equal to a 1. Now I'll skip this one above because these are going to apply to pretty much all logarithms if they follow that same way. And we'll look at the properties in the next video. But if I have log of 100, log base 10, because it's a common log of 100, is going to equal 2. And we want to just justify why is that? Why does this come out to be 2? And it's because if I converted that to exponential, that would say 10 to some power has to equal 100. So what would that power be? 10 to what power is 100? It's 2. Same situation here, log base 10. So we're saying 10 to some power is going to equal 1,000,000. So we got to figure out what 10 to what power is going to be 1,000,000. Well, there's 1, 2, 3, 4, 5, 6 zeros. So that'd be 10 to the 6th power. So log of 1,000,000 is automatically equal to 6. And then we have log of 1/100th. So that's asking 10 to what power is going to equal 1/100th. Now, if you remember when we were graphing these, we saw we got those small fractions when we were going into the negatives. And so this is negative exponent something. So 10 to what power is going to be 100? Well, we just saw that in the first one. 10 to the 2nd power is 100. So that'd be a -2. So we know automatically that we would have something like this. These are going to follow the same kind of situations. So if I had a different base and said log base 2 of 8, and we don't know what that is, we're trying to figure out, and we would say, oh, well, that's 2 to some power is going to equal 8. What would that power be? Well, 2 squared is 4, 2 to the 3rd power is 8, so that's automatically going to be a 3. If we had log base 3 of 81, we want to know what that equals, we would be asking ourselves 3 to what power is equal to 81? Well, 3 to the 1st is 3, 3 squared is 9, 3 to the 3rd is 27, 3 to the 4th is 81. You could do that with natural logs as well. It would just be e to some power. All right, so we can use those properties to solve these. In this next video, we're going to actually work through these and try these out.